Hi, my name is Nease, and this is a presentation for GRC 605, Unit 2, titled Visualizing Hypothesis Testing. In today's presentation, we are going to look at several possible visualizations for hypothesis testing. The first example, we're going to look at a bell-shaped curve that will allow us to test whether action is needed or warranted in a production setting. The second example, we're going to compare two data sets to compare one team against another. The third example will help us understand efficiency in order to appropriately resource a team or situation. And the fourth example, we're going to look at a scatter plot to determine if there's a relationship between two variables. So visualization number one represents a bell-shaped curve, meaning that it has a symmetric distribution. The mean and the median are the same. If we wanted to see a less symmetric distribution, the mean and the median are not the same, and we refer to these kind of curves as skewed. But for the purpose of this visualization, we're going to test for a mean. You'll find that the x-axis is a little confusing, or certainly was for me, because in a lot of 100 it's not possible to have a negative number of defective widgets. So I found that the key to interpreting the research question are the words on average. So for this particular exercise, I put myself in the shoes of a quality assurance leader at Acme Widget Company. And I imagine that I had just started my role and was given this visualization to evaluate whether changes need to be made to the production of the widgets. Again, the key words in the research question are on average. The null hypothesis for this analysis suggests that all widgets are defect-free, which we know from experience is practically impossible. So the focus I will place is on the alternative hypothesis. The bell curve suggests that in a lot of 100 widgets, there is a 40% chance that on average we will have 0 defective widgets. Then it goes on to show that there is a 25% chance that on average, one widget in a batch of 100 will be defective, a 5% chance that on average 2 out of 100 will be defective, and nearly no chance that 3 or 4 out of 100 will be defective, which is probably pretty good. This provides sufficient evidence to reject the null hypothesis and explore whether quality improvements are needed or whether the defect rate is fine and acceptable. Visualization number 2 serves to compare two groups represented by two curves. These two groups are two baseball teams. The blue one is a major league and the red one is a corresponding minor league. And so let's assume that each team has 20 players, meaning 20 equals 100% of the team, irrespective of if they're majors or minors. The y-axis shows a distribution of home runs for a given time period, and let's assume that it's for a season. And the x-axis shows the distribution between 0% of players and 100% of players, represented by the number 1 on the x-axis, although we don't actually see that number being visible in this particular diagram. But if it was, you'd see a tail out to the other side. So assuming 20 players per team, each player represents 5% of the team. The minor league curve shows that the mean number of home runs for the minors is 15 home runs per season, with even distribution both sides of the curve, although we do not see the tail, meaning that there are many players on that team with no home runs at all. The blue curve, which are major league players, shows that the mean of home run per season is 16, and the mean on the minor league team curve, however, corresponds to approximately 29% of the players, versus the major league team, who not only has a greater percentage of team members being hitters, but also fewer team members per team that have not hit a home run at all. So this translates to the confirmation that there is a difference of approximately 7% between the number of hitters on a major versus a minor league team, showing very clearly that there is a difference that warrants further exploration. Visualization number 3 is an efficiency comparison, and it's useful because it allows us to make a decision around achieving a goal with the fewest resources possible. So looking at the mean efficiency of both teams, we can see that the red team serves approximately 30 people per hour, and the blue mean is approximately 50 per hour. So while the blue team takes longer to serve the total population as opposed to the parallelized red team, we can clearly see that there is a difference in efficiency, thereby rejecting the null hypothesis and warranting further explanation into what is the appropriate mix to look at both efficiency, but then balancing that off with customer satisfaction. Visualization number 4 is a correlation test, and it serves to generate a hypothesis that is derived from a correlation of two variables, in this case weight of a vehicle and its miles per gallon. We are looking to see if there's a relationship between the two variables, and if so, are the correlations meaningful. So in the scatter plot, the x-axis represents miles per gallon, and the y-axis represents the weight of the vehicle. If we draw a best fit regression line through the middle of the scatter plot, we can see that as the vehicle gets heavier, and this is somewhat predictable, it gets less miles per gallon of gasoline. So, and what we also see is that there are roughly the same number of points below and under the line, which is kind of what we want. So we can clearly see that the relationship between weight and fuel consumption is the right research question to be asking here, and that the null hypothesis that there is no relationship clearly is invalid. We can see from the calculated p-value of 0.0001 that there is only a very small fraction of percentage chance that the relationship is coincidental. So what are some of the important takeaways from this visualization presentation? One, that labeling the X and Y axis correctly and really thinking through what we're measuring is key to understanding visualized data and creating a hypothesis test that is practical and actionable. Where data is missing, certain assumptions need to be taken into consideration. So for example, where I did with the baseball team, where I needed to make an assumption of the size of the teams being equal, although that was not stated anyway, as well as the number of home runs within an equal given time period. And the actual use of the visualizations to represent data, I think, is highly viable, particularly as a first kind of rough cut measure, way to look at various research questions, again, at super high level. I think it's possible to at least rule of thumb accept or reject the null hypothesis by simply looking at the visualized data. However, I think it's premature to make a complete determination without further exploration into whether it's a sensible investment to look at the analysis further and also to measure how much differentiation there actually is. So with that, I'd like to thank you for your time and am open to any questions. Thank you.